Inheritance is one of the foundational pillars of object-oriented programming, and it is all about reusing code efficiently. Let's look at a common problem. Without inheritance, if you have a car, a truck, and a motorcycle that all share basic behaviors like needing to start and stop, you would have to copy and paste the exact same code into every single class. This creates a massive maintenance risk. If the logic for starting ever needs to change, you'd have to track down and update it in every location manually. Inheritance completely solves this by allowing us to write the shared code once in a central location. Then, all those related classes just access it automatically. To make this intuitive, think about the evolution of a family business. In the first generation, a grandfather establishes a general vehicle business. He sets the absolute foundational rules that every vehicle must have an engine, wheels, and be able to move. Next, the son inherits this business to specialize in cars. He doesn't throw away his father's rules. He keeps them and simply adds new features like air conditioning and doors. Finally, the grandson inherits the car business to specialize further into sports cars. He keeps everything from the previous generations and adds turbo engines and racing seats. Notice how they continually build on the existing foundation without ever rewriting the basics. That is exactly how inheritance works in code. When we write this in Python, there are four essential terms to know. First is the parent class or base class. Think of it as the original blueprint containing the shared variables and methods. Second is the child class or derived class. This is the new class that inherits from the parent. It gets all the parent's functionality for free and then adds its own unique features. Third is the super function. This acts just like a bridge back to the parent. When we are inside the child class, calling super.init tells Python to cross that bridge and run the parent setup code so everything is initialized properly before adding the child's specific details. Now that we understand how these generations of classes relate to one another, let's look at how this hierarchy maps out visually in a full structure. Let's see how this hierarchy actually looks in practice. Right here at the top of our tree, we have the parent vehicle class. Think of this as the blueprint that holds universal features. It contains shared methods that apply to any vehicle, like starting, stopping, and showing info, along with basic attributes for brand, model, and fuel type. As we follow the arrows down, we reach the first level of inheritance. Here we have two distinct child classes, the car and the truck. Notice what's happening here? Both of these boxes specify that they inherit everything from the parent above them, but they also specialize. The car adds a honk method and counts the number of doors, while the truck adds the load cargo method and tracks its capacity in tons. We can go even deeper. Down at the bottom, there is a third level, the electric car, which is a direct child of the car. This is a great example of multi-level inheritance. The electric car inherits features from the car, which in turn inherited from the vehicle. It gets all those previous abilities, but it adds its own charge method and battery capacity. It also does something special. It overrides the fuel type to explicitly be electric. To see why this is so powerful, let's look at a real industry example with Tata Motors. Engineering teams here use a base vehicle class to handle universal, tedious tasks like registering the vehicle or setting up service reminders. When they develop a specific model, like a truck or a standard car, they don't have to rewrite those core functions. And when they introduce an electric vehicle, the team only needs to write the unique code, like the battery recharging logic, while automatically inheriting the rest of the car's standard proven code base. This exact same principle applies beyond physical objects, right into software engineering. Take the Django web framework, which powers massive platforms like Instagram. Django gives developers a base model class that contains all the incredibly complex logic needed for saving and loading data from a database. When a developer needs to create a user profile or a post, they simply inherit from this base model. They only define the specific fields for the profile or the post. The actual heavy lifting of communicating with the database is inherited automatically. The main takeaway here is that inheritance allows data and functionality to flow downward,
preventing redundant code and leading to much faster development. Now that we understand how these family trees are structured conceptually, let's step into the code and see exactly how we write that foundation.
Let us see how these inheritance concepts actually come to life in Python code. We'll start right here with our foundation, the base class. This is the vehicle class. Inside it, the init method sets up the fundamental attributes that any vehicle in our system would need to have, which you can see visually represented here as brand, model, and fuel type. This base class also provides shared behaviors for all vehicles, like starting the engine or showing information. Now watch what happens when we want to create a more specific type of vehicle. Let's look at the car child class. We tell Python it is a child by putting vehicle right here in parentheses. This means the car gets all the features of vehicle automatically. But look closely at its setup. This line with super dot in it is absolute magic. It tells Python to go up and run the parent vehicle setup code first. Because of this, the car class doesn't need to rewrite the basic assignment code for the brand, model, or fuel type. It only has to worry about its new specific attribute, which in this case is the number of doors. We can use that exact same logic to create a truck class over here, adding things like load capacity. But let's take it a step further with a grandchild class. Down here in the bottom left, we define an electric car. Notice that it inherits directly from car, not vehicle. When it initializes, its super function triggers a chain reaction. It calls cars init, which in turn calls vehicles init. Also, since every electric car uses batteries instead of gas, we don't need to ask the user for it. We can just hardcode electric as the fuel type. Let's put this into practice and create some actual objects in memory. In our test section, we create a standard car, a diesel Toyota Innova, and an electric car, a Tesla Model 3. You can see their specific data stored right here for the standard car and here for the Tesla. Now here is the real power of inheritance shines. When we run tesla.showInfo, how does Python know what to do since we didn't write that method inside the electric car class? Let's trace it together using the method lookup process on the right. First, Python looks inside the electric car class. Is showInfo defined there? No. So it travels up the hierarchy to its parent. It checks cars class. Still not there? Finally, it moves up again to the grandparent. It looks in vehicle class, finds the method, and successfully runs it. This walking up the tree means we only had to write that showInfo code once, but objects at all three levels can use it as if it were their own. The key takeaway here is that inheritance allows child classes to automatically inherit behaviors from their parents while using super to seamlessly initialize shared attributes without duplicating code. As we move forward, we'll see how this exact same logic applies to real-world software architectures. Building on our previous example, let's take a moment to recap the core ideas. Inheritance is a powerful concept that allows a child class to access and build upon the attributes and methods of a parent class. Think of it like a structural foundation where the essential traits flow downwards into your specific classes. We use the super function inside our child classes to maintain this connection and pull in that initial setup automatically. To verify your understanding, let's look at a few quick scenarios. First, imagine you are building a banking system. The generic account would act as the parent. The child classes like savings account and loan account would inherit the basics but add their own specific features, for example, interest rates for savings or repayment schedules for loans. Second, remember that calling the super initialization function is critical. It ensures the parent class actually sets up its data. If you forget to call it, your code will crash when you try to access those variables because attributes like brand or model were never created in the background. Third, what is the difference between inheriting and overriding? Inheriting a method means you are reusing it exactly as the parent defined it, without changing a thing. Overriding a method, on the other hand, means you rewrite it completely so that it behaves differently for that specific child. Now it's your turn to put this into practice. You are tasked with building a media system. First, you will create a parent class named Content. This blueprint will hold shared attributes like title, creator, release year, and a general describe method. Next, you will create three distinct child classes like movie, podcast, and song. As part of the requirements for this problem, each child must call super init, add their own specific attributes like genre for a movie or an album for a song, and override the describe method to print their exact details. Completing this code exercise will demonstrate your ability to reuse a foundation while extending it for specific needs. Why go through all this trouble? By mastering inheritance, you move from writing isolated scripts to building highly scalable systems. You can define a general concept once and create infinite variations of it with minimal extra code. This not only makes your development process much faster, but also ensures that your code is cleaner, easier to update, and more professional. You are now prepared to build robust, complex object hierarchies in your own applications.